thanks for the introduction, Sharon. So I have changed the title of this talk. So previously, I thought it was a good idea to introduce some important technical details. But then our group members reminded me it's better to give an overview of the progress of this project. So right now, the title is similar to the title of our Caltrans peer project. And for this project, we have Professor Kenichi Soga as the PI, Professor Tracy Becker as the co-PI, and I'm also the co-PI. And Bingyu Zhao is our collaborator, and Peng Junli is our graduate student researcher. So as expected, most of the works are done by Peng Jun, and thanks to him, we have a lot to share with you today. So the objective of this project is to develop simple computational tools to determine which bridges should be designed as recovery bridges on a highway network. So here the keyword is actually simple, because as required by the Caltrans, they want the computational tools to be implemented into Excel. So it's like, the agent-based modeling is kind of difficult to be implemented into Excel. So then we needed to figure out alternative simplifications. So to achieve this research objective, we have decomposed the project into 4 components. So we have we needed to develop an importance measure for bridges. So the importance measure will be used to rank the bridges. And also we needed to develop a method to identify corridors. So the idea is that we might have a multi-scale decision-making process. So we try to figure out those critical corridors, and then we find the critical bridges on the critical corridors. And the third part is the verification on the highway network of the Bay Area. So the highway network of the Bay Area is considered as our simulation test base. And finally, we needed to do some software package development for Caltrans. So currently, the previous 2 items are done, and the verification is almost done. And for the software development is still ongoing. So like I said, the first task is to develop an importance measure. So how to define a critical bridge? And our approach is we think a critical bridge should be vulnerable to earthquakes. So that is kind of straightforward. And the second criterion is that the critical bridge should also be important for transportation functionality. So the idea is that you might have a bridge which has a large failure probability, but the bridge may not be critical for the transportation functionality at a global level. So the idea is that if we want to define a critical bridge, it should satisfy these 2 criteria. So it's easy to fail, and also it's important for a system level performance metric. So to determine the vulnerability to earthquakes, we just need the failure probability. So that is a component level measure. Because to compute the failure probability for each bridge, we do not need to consider the failure probability, for a nearby bridge. We can consider them one by one. So it's a component level metric. But for the transportation, for the system impact of that bridge, that is a network level. Because the failure of one bridge might have some cascading effect or rippling effect. So it might have a system level impact. So eventually the importance measure we designed is we just use failure probability multiplies some quantitative measure of system impact. So for the failure probability part is kind of straightforward, because we have the performance-based earthquake engineering, so we just use the fragility function to compute the failure probability for all bridges on the highway network. And here we adopted the USGS Earthquake Hazard Toolbox to assign the fragility functions for all the bridges on the highway network of the Bay Area. So for the system impact is kind of non-trivial. So because we want to measure like what is the impact of the one bridge on a system level, transportation functionality. So the brute force approach is to perform percolation. So it's like we fill one bridge and we run an agent-based model and we try to figure out what is like the mean travel time reduction. So this is percolation, but it's computationally very demanding, and somehow it contradicts our main objective of developing simple tools. So eventually we have spent a lot of time trying to develop a so-called simulation-free method. So here, it's not really simulation-free, but it's just not based on agent-based modeling. So I'm attempting to show those interesting mathematical details, but I guess it's better to not do it here. So from a very high level, this simulation-free method is just a mean field approximation to the heterogeneous traffic flow problem. So we tried, this is inspired by the page ranking used by Google to rank those websites. And also is inspired by some statistical physics approach of constructing mean field approximation. So the final output of this simulation-free method is the probability of visiting each bridge. So the assumption is that we use the visiting probability as a system impact. So the assumption is that if a bridge is visited more often, then it is important. So, well, of course, it's an assumption. It may not work for some very rare event, but right now this is what we have. So the computational flow looks like this. So the simulation-free method takes in the origin, destination, distribution, and the network topology as the input. And the output of this method is the bridge visiting probabilities. So we use these bridge visiting probabilities as a measure of system impact. And then we multiply this system impact by failure probability. So we get a risk-informed importance measure for each bridge on the Bay Area. And also, since we have the simulation-free method, so we have the tool to rank bridges, and we also needed to consider corridors. So like I said, we might have a multi-scale decision making. So we want to identify the critical corridors and then the critical bridges on the corridors. So here we consider two types of corridors. So the first type is the critical facility access corridor. So the idea is that suppose there is a large earthquake and the regular commute pattern will be destroyed. So people just want to get access to those critical facilities like hospitals, like airports. So this is the idea of critical facility access corridor. And we also have the high volume corridor. So this is for the scenario like the earthquake is not that large, so the regular commute pattern is still there, and we just want to identify the high volume corridor that will be used by a lot of people. So for the critical facility access corridor, of course, we needed to define critical facilities. So here, after a lot of discussions with Sharon, and finally we come up with a list of the critical facilities. And we further sub-partitioned those facilities into two groups, like type A, which is only for hospitals, and the type B are for fire station, police station, and others. So there are some detailed difference in trying to determine the critical access corridor for type A and type B, but the general principle is that we assign the critical facilities as the origin or destination, and some uniform grid points as the destination and the origins. And also here, to identify critical critical facility access corridors, we have considered equity by not like doing weighting by population. Because you know, if we weight by population, the majority always wins. So if you are living in some remote area and you only have one bridge that gets you access to the critical facilities, then that bridge may not be ranked as critical if we average over population. So here we consider this equity so that those bridges will be still ranked as important. So for the high volume corridor, we just assign the daily commute origin destination as the input of the model. And we further need some partition or clustering methods to cluster those highway network into small parts of corridors. So here there are a lot of methods like distance-based clustering, graph-based clustering. And here in this project, we developed a kind of a simple interchange-based clustering. The idea is because the highway network is typically, topologically simple. So we can just identify those interchanges and just assign all the bridges between two interchanges as a corridor. So the figure on the right is the clustering results of the corridors. And then we apply our risk-informed metric to find the critical corridors. And here I will share you some of the simulation results. And for the 225-year return period earthquake, we have found the 10% high rank bridges for the access of hospitals. And on the left, it shows the results from the equity-based weighting. So it means we do not weight by population. And on the right, we have the population-based weighting as a comparison. So the difference is actually, it's not, let me see if I can. So the difference actually lies here. So if you see, if we use equity-based weighting, we still have some critical bridges in this area. And if we average over population, then the critical bridges are more concentrated. And also we have considered this 975-year return period earthquake. So the results are more dispersed because, as expected, if the earthquake is larger, there will be more bridge failures, so that failure probability might play a more important role in that risk-informed metric. And also we can rank corridors. So here is the result of 10% high rank corridors. And on the left, we show this for the access of hospitals. And on the right, we show for the other facilities. Also they are critical facilities, but they are not hospitals. So here also this is the 10% important corridors under that earthquake. Okay, so for the next steps, we are considering to do more simulation and verification, and also we will continue developing the software package. And there are still a lot of technical issues, but we still have 1 year to go, so I think we can figure them out. So yeah, thank you very much.